Hello and welcome. Today we're going to learn how to achieve in pure HTTP reversal and TCP handshake handling. Additional, we are going to transfer all the data from the server to the client through a personal RSA algorithm which will eventually encrypt all of the data in one side at the sender, which is the server, and in our client we will decrypt it through the same personal RSA algorithm. So we know it's a reversal. So at the left side the computer icon represents the server, at the right side the computer icon represents the client. If it's a reversal, the server needs to start with its SYN packet, and the server starts with the TCP handshake process. We can see that he's sent the first SYN over here. It's because he will eventually the reason he sent and he wished to start with the handshake process. It's because he wished to send an HTTP packet which have inside it data section with the hello word in order to identify. So in order to make it possible, first you will need to start with the TCP handshake process. So he sent to us, we are the client, a SYN packet which is flag is 02. He got the options, he got sequence number randomly that he will send to us, and its ACK number meanwhile will be zeros. Of course, we have a source port and destination port. I put those variable values because if we are dealing with fully construction with our raw socket in the client side, we will need to deal with it without the kernel assist, and we will need to follow the values and to increase them according to the session, and to fill inside him the accurate flags. So the client side, okay, will respond with SYN-ACK if you wish to continue with this TCP handshake. We will create our options section, and of course we will take the sequence number to our acknowledge section. We will increase it by 1, which will eventually tell to the server that okay, we got it, and let's process with my packet right now, which I will send to you, and we will create a randomly sequence number to send to the client, to the server, sorry, and of course we will keep the destination and the source port in order to make this connection live and reliable. Next, the server will send to us and push ACK, which will do a packet which will do 2 actions in one packet. The first action is to finish with the TCP handshake process. We will establish the connection, and the next action is to send an data, in our case it's some data in our HTTP protocol section, which will identify itself by the hello word. Okay, so in our side we will get this packet, and we will know that this is our word pass for the beginning. So we will acknowledge this packet, okay, we got with the ACK flag, okay, and then we will start with the reversal, and we will send to the client, to the server from the client, an HTTP request for JPEG content, okay? And inside it, we will inject our CMD request, which is gonna be encoded in 16.4 in base 16.4. Of course, when we are going to send some data, it's going to be, if it's a request, HTTP request, the flag needs to be in push ACK mode 18 and to follow the sequence and the ACK the ACK values. Here we can see that this is the first time in our ACK section we increase the value by the data we got, okay, from the server. We can see it over here. This was the first time, okay. We took the sequence number we got from the server, okay. Just a moment. Here we go. We took this sequence number and we increase it by the amount of bytes we got from our HTTP data section, okay. If you will not increase the value by the amount of data you got, the server will send to you the delta in bytes, the same bytes in its data section of what you sent to him in your acknowledge number. So you can eventually, if you will not follow and you will do an accurate numbers to your sequence and acknowledge number, you will have a lot of retransmission, or you will eventually make this connection slow and it will not be efficient. So at the last step, when we start the reverse shell, we are going again to inject our CMD request, in our case, into our HTTP JPEG request, and it's going to be encoded in 16.4 in base 16.4. Next step, the server will get the CMD request, right? The JPEG request, and eventually we will need to extract the CMD command request from its header. It will run it through the subprocess and save the output. The next step is to take the output in ASCII and to split it into 1 byte values, and then convert each byte value to an integer and store them into the dimensional array. Next, we will call the Perosnal RSA algorithm we created last videos with 2 prime numbers and save the return back values, the encryption key, the decryption key, and the end values. As we know, RSA algorithm, RSA encryption is an asymmetric, meaning we have different key to encryption and different key to decryption. Next, we are going to encrypt each value inside our 2-dimensional array through the RSA algorithm method with the values we got, which is the encryption key and the end value, and then we're going to store all of our encryption values into one string, which will separate each encrypted value, encrypted result, by question mark. What I mean? Let's see. Let's say we have 2-dimensional array, okay? We have the integer number 11, 12, and 14. Next, we encrypted each one of them. Let's say that 11 will be represent as follow. okay? 12 will be as follow, and 14 will be as follow. The next step is to convert them to string, okay? Before we are going to combine them together in one string. And the final step, as we saw, we will have a string which will have question mark between separate each encrypted value we got. So let's put them together. Okay. And the last value with another question mark, and then we're going to close it. The next step is when we got our encrypted string with its all encrypted values, we'll need to inject this string into our HTTP response inside the JPEG content, okay, with another marks which will tell to the client where is the start of its encryption data and where is the end. So first we will have in our JPEG content and reliable, right? Reliable extra string. So we will have something like almost 1000 of reliable string. Let's say I don't know. Let's say we have reliable extra string, okay, with 1000 bytes. Then after this 1000 bytes, we are going to we're going to add start marks and end marks to our encrypted text we're going to inject inside. So it will be as follow, okay, and we're going to inject our encrypted string, and we're going to add another signs to tell the client that this is we are going to mark its end of our encrypted text, and of course to make it reliable we're going to add the extra string which is going to close the JPEG header, okay? So this is not the end, okay? What we are going to do next, we need of course additional to inject the JPEG content, the encrypted text. We additionally will need to inject our decryption key and the N numbers into our HTTP response, and you will see it at the HTTP response header, okay? At the content we put our encryption string, and at the response header, okay, at the response we are going to inject our decryption key and the N numbers inside our server name, okay? Let's say this is our server name, and you will see over here and over here the client will need to deal with the numbers, if it will be 2 bytes, 3 bytes, 4 bytes long, to the n numbers as a decryption number, you will see the little mechanism I wrote in order to make it reliable. So after we inject all of our encrypted data and the decryption and the end values, we're going to split our HTTP response, okay, into 1000 packets of bytes, and to send it to our client. So this is the server side. What the client side will need to do? We have a lot of work because it's fully construction mode. We need to get the HTTP header response first, right? We are going to extract the JPEG content length first in order to know to how many bytes we will need to open a buffer and to save all the JPEG content completely without any errors or problems, right? And how we're gonna do it? We going to do it through a couple methods. One method is the length of the HTTP content. In each packet we will get, we'll need to calculate each time the number of the bytes we got and to decrease it from the buffer. Of course, we will need to follow the sequence and the new ACK numbers we get and we send, and we can calculate the last sequence and ACK numbers we will need to get from the server, and that's how we will know how to measure correctly and to follow the server response packets. Of course, we will see it next. I will explain it through Wireshark. We will see it live, the example and the code I wrote. Next, each time we'll get the HTTP response with the JPEG content, we'll need to combine all the content data we got from the server and to put it into one string, of course, as we got it. And after we got all of its response packets, we will get the JPEG, right? We will need to search inside the JPEG where we have the start of the question mark and where we have the end question mark, where we have the signs of the start of our encrypted text and where we have the end, the signs which will represent the end of the encrypted text. Okay. Next, after we know where is the start and the end of the encrypted text inside the buffer, we will need to extract the encrypted text. Okay, and we will finally store each value inside our encrypted text inside two-dimensional array. So let's see, we know that our encrypted text will be as follow, right? And we will put it into two-dimensional array, which will store with the same order which the question mark is represent the order between each value, and we'll keep their orders of the values. Very important, because otherwise you will get, when you will decrypt the values, another differently output from what you sent in your request, CMD request. So now we got our two-dimensional array. Then we will call the RSA algorithm and we will decrypt each value with the decryption key we got and the N number. Okay, so we'll need to get the same values as before the encryption, and it's depend on your RSA algorithm and how accurate it is. And we learned at the previous videos how to get as much as we can an accurate result, because when you create encryption keys and decryption keys, you will have a lot of combination, and you can eventually do a lot of verification process, and then you will have an accurate decryption and encryption keys to your RSA algorithm. So you can follow my previous videos to see it. And after we got the decrypted values, we are going to convert them into an ASCII. Okay, and let's say A, let's say B, let's say D, and then we're going to combine them together, and we'll get the output of the CMD command. Of course, it needs to be very fast without any errors or problems, and that's what we're gonna learn at this chapter. So this was the brief of our HTTP reversal. Now let's start with take a quick brief of our codes in our server and our client, and then we will explain each code, and we will demonstrate it. Let's take a quick brief of our codes. We will investigate the client side and the server side. Then we will run the reversal itself, and we will go each step by step and investigate it deeply. So let's see our client side, which is the most complicated, because we are using fully construction mode without the kernel assist. So we need to provide all of the construction from the IP layer. It's including the checksum for each time we're sending packet, the IP checksum and TCP checksum. It's an additional the IP values, header values, and the TCP header values. If it's the sequence number, if it's the ACK number, if it's the total length or the header length of both layers. So here we can see our client side. We can see that we configured the socket, the raw socket. We're using raw socket, and its protocol is IP TCP. We tell the kernel don't assist us. Okay, we will use full construction, and first we can see the definition of the IP protocol. We can see here all the variable values, which most of them beside the total length will be constant, because we are using the same IP address, destination and source. We are using the same protocol number, which is 06, symbolize the TCP. TTL same, and you can see that the dynamically variable value is the total variable, and of course each time we will need to calculate the checksum. So as you remember, the last videos, in each video I repeated it. Yes, I'm using own personal algorithm to calculate the IP checksum and TCP checksum. I'm using the binary method. It's just for you to exercise more and more Python coding with row socket subject. We can do it more easily way with the hexa method, but I prefer meanwhile to stay with the binary method. So let's see, this is the IP method, function. We will discuss it more later deeply. So finally this function will return the IP header after we packed it, okay, and after we have all of our variable values correctly. Each time we are going to send something on the error, okay, if it's if it's during the TCP handshake process, or if it's during the session itself. If we are exchange data between us, it will be must be involved with this function. Each time we are calling to one of our TCP TCP function you will see below, we will need first to call to this IP function. So you can see that this IP check, it will be for preparation to the IP checksum, as we learned in the previous videos. And last one for the IP is the packed data for the IP, and that's all for the IP header and its functions. So next we can see the first TCP function is for the SYN-ACK. You can see that most of the data over here is constant, because the first time we're gonna reply with SYN-ACK, we will have an constant options, which is customized. Anyone can point what is preferring, and the variable values which are not constant in our TCP SYN-ACK function is the destination port, which we gonna extract it from the SYN packet from the server, and the sequence number, which we are going to calculate it and then to put it in our acknowledge number. Again, we are going to take the sequence number from the server packet and then call to this function. And of course, you can see over here we are calculating the length of the total TCP we have, and with our total TCP and IP. Okay, I will fix myself. In order to find the total IP length, we will need first to calculate the TCP header, okay, and its data, and then and just then we can call to the IP function with the total length value we found, and of course we will increase it by 20 because the IP header is constant in our case with 20 bytes. Okay, so next we can see that in order to calculate the TCP checksum, we'll need some of the variable values of the IP header, which is the destination address, the source address, and the protocol number. So we call to another function method which is going to do the work for us. Next, we are going to calculate for the TCP checksum the real length of our TCP header and data, okay, and then again we are going to call to the function TCP1 checksum, which is going to prepare our variable values, convert them to binary, and will and will, of course, as you saw at the previous videos, will complete its zeros according to their length on the left, of course. Next, we can see over here that we are calculating our checksum, TCP checksum, and finally, when we have our TCP packet, we will return to where we to the point where we call to this function. We will return the TCP packet data after all the calculation, and of course the IP packet data. So now we can see next, it's the next function is the TCP for the push flag, which we are going to exchange data. So here we can see that we will need to provide to this function couple of variable values. The first one is the acknowledged number, which we will take from the sequence number, and we'll calculate it, of course, if we will during the session at the packet of the server we will accept some data. We'll need to increase the sequence number with the with the amount of data we got on the same packet, and then to put it on the acknowledged variable. Next variable value is our sequence number, which we are going to take it from the acknowledged number of the server packet. Next, the port, which we are going to take from the TCP destination port, which is the source port of the server. From its packet we are going to extract it. Next, we have two variable values. One of them is the data itself, and the second one is just a moment. The second one is the data, okay, we are going to send in one string variable value. When we will investigate more deeply this code, I will explain it more clearly. Okay, for now we can just avoid it. So next we can see that we are calculating the total TCP length, of course, in order to call to our IP function with the accurate IP length. Again, we will need the destination, source IP addresses, and the protocol number. Okay, next we are going to calculate again the TCP checksum, and we're going to finally to get the TCP push packet in pack data, okay, and just then we can return it to the same point we call it. We are going to return three variable values. One is the IP packet data, second is the TCP packet data, and the third is the length, okay, of the TCP header and data. The third TCP function is the ACK, which we will need to ACK some packets we get from our server side. So over here we can see that we need to provide three variable values. One of them is the acknowledged number we need to calculate. The second one is the sequence number and the third is the port number. The same process, we're going to prepare the TCP checksum variable values, and of course we are going to calculate the total TCP length, and just then to call to the IP header data, the IP function data. Next, we will return the TCP packed data and the IP packed data. Over here we can see the functions which will prepare for our TCP CNAC the checksum variable values. Okay, when we are sending the CNAC, we will need to provide the options. Okay, you can see the same, almost the similar functions, just for different TCP flags functions. Okay, if it's the push, if it's the CNAC, if it's the ACK. Next, we can see here the first thing that we will need to do is to, because it's fully construction mode, to enable the three-way handshake. So if you can see, we will get from that specific user with its IP address and with the port we are listening to. Okay, this is the destination port, which is 18 in decimal, and if we are getting SYN request, then we will extract the sequence number, right? We will increase it by 1, put it in our acknowledge number, and we will call to the TCP function, which going to the SYN ACK function, which is going to calculate itself, and then return to us the TCP data pack data and the IP pack data, and just then we are going to send a SYN ACK. Next, if we are going to send it, we are going to break the endless loop and open another endless loop. We are going to listen, and we will need to get, after we send a SYN ACK, we will need to get the push according to this plan. Okay, with the push ACK, as I told you before, it will provide the data in one packet, and of course in this packet we will establish the connection, will close the process of the three-way handshake. So if we will get to the same port we are listening, which is 80, with the IP address we are willing to get from, with TCP flag, which is push ACK 18, with the word path, which is hello, which we are going to take from the TCP data section, and of course if the acknowledge number is equal, if our acknowledge number is equal to the sequence number we will get from the server. So it's just another way to make this connection reliable. So if it's all this condition will be true, we are going to do the same to extract the sequence number, to calculate its new acknowledge number, because we already got you can see the hello data. So we are going to calculate it, and then just then call to the TCP3, which is the ACK TCP function, and we will send an ACK finally. So if it will be true, we will break it and we will go under to the start of our reverse shell. So from here, this is our reverse shell, which will never be end until we will exit or the client will close its session with us. So the first thing we will do, we will ask from the user to put some command in order to run it and send it to the client, we can see that we will inject this command after we encode it to base 16.4 in our HTTP header. Okay, just regular header. You can change it to according to your environment, and before we are going to send it, we are going to we have some calculations over here. We are going to split this header, HTTP header, for two values, for two bytes long values. Okay, why I did it? It's because that it's for my TCP checksum. I prepared this data for my TCP checksum, so this is why I split all of this string, the ASCII string, into 2 bytes values order, and we can see here all the calculations. It's not really big issue, but you can do it in different ways. I will explain it more deeply when we touch it. Just then, after we will prepare our TCP header data, we can send it to our server with the TCP2, which is mean TCP push ACK, which eventually we're going to send this HTTP request with our CMD inject into our HTTP header. So after we send it, of course, the server will need to get it and to do its calculation and the encryption on the data with our personal RSA algorithm. So let's open the client, the server side. We can see it's not long. It's not long because in the server side I didn't use fully construction mode. I just use a regular TCP sock stream. As we can see, it's not a raw socket on the server side. Okay, so there is an advantage and a disadvantage, of course, but in the client side, the most important thing to me was to encrypt the data. Okay, and with our private RSA algorithm. So let's see what we are going to do. The first thing, as we saw, we are going to connect to our client, which this command will do. In one command, it will do the three-way handshake, and what you saw until this line, okay, it's three-way handshake. You can see the difference between fully construction mode and not fully construction mode, even if we talk about not raw socket, because we use regular TCP in our socket type. So you can see what you will need to do in order to make it reliable, and if you wished, it will be almost 100% automatically without any errors. So you will need to investigate and to do it with accurate writing. Okay, so you will have more easy life to do it. You will not have any other difficulties. So we can see that until this line, it's all of the TCP handshake. So in one line, which is beautiful, we can see it over here. The server did it in one line. Next, we are going to send the hello word pass, and we can see on our client side, if we will get the hello, we are going to acknowledge it, of course, and just then we can go over to our reverse shell. Finally, So after we send our HTTP header request with our CMD command request, you can see that the server side will accept it, and the first thing it will do is to extract the CMD command from the HTTP header and to decode it to regular ASCII string from base 16 form. The next thing is to do, of course, is to run this command we extract. So we are going to open a subprocess and we are going to save this output in our variable. The next thing, as we know, we will take the ASCII string of our output, right? And we're going to split it to 1 byte values. So how we're going to do it? You have over here the calculations. We will touch it more deeply later. So we can see over here that we are going to split it to 1 byte values and to store it in 2-dimensional array. Okay. Next, we are going to call. Okay. Sorry. I just opened the old client. Client code. So just a moment. Okay, let's see. So as we saw, we're going to take each byte from our ASCII output and put it in our 2-dimensional array. Very simple. You don't have to do any calculations over here because it's just 1 byte, and you will not have any mistake if you will do the for loop in the range of all of your ASCII of your ASCII digits. So next thing, as we spoke, in order to encrypt it, we are going to call to our RSA algorithm, personal RSA algorithm, with two prime numbers. The third number is just a number to check our is number to encrypt just and decrypt, just for a verification, another verification of our RSA method. As we saw in the previous videos, we will get multiple combination of decryption and decryption keys, and our RSA algorithm will find the best combination which will provide an accurate encryption and decryption for our values. It's very important because you wish to get clearly string without any problems or any issues. So it's very important to use all of your keys in order to find the most value for you. So as you saw, I used small prime numbers because I didn't make it very fast for high prime numbers. I will need to learn additional techniques, but the mathematical methods are very accurate, and you will see the result by yourself. Later we will discuss a little about the RSA. We'll open it, the private RSA algorithm. Okay, next, after we got the encryption and decryption and values, we are going to encrypt our 2-dimensional array with all the values we extract from the ASCII, and we, as you can see, we convert it to an hexa and then to decimal, to integer. Then we are going to iterate according to the encryption key we got and the N number we got, and we're going to encrypt our variable values into our two-dimensional array. The last step is to store them in one string, which between each and each number we result, which is encrypted value, we are going to wrap it with two question marks in the beginning and at the end. This method I copy from my private RSA algorithm, so you can see it's very simple to do the action of the encryption and the decryption. So the next thing is, of course, is to inject our Q22, which is the one string of our encrypted ASCII output. So as you can see over here, we have a reliable, which is start with FFD8, reliable JPEG content, okay, which is start with FFD8, and just after, you can see, after more than 3000 bytes, okay, we gonna construct the H10, and then just then we are going to inject our string, encrypted ASCII string, which is going to be representing numbers, and we will end it with this symbol, and of course we will need to end it with FFD9 to tell to the client, and of course to tell to all the devices that see it that we finished with our JPEG content. And of course we will need to be accurate, so we need to measure the length of our HTTP header and content. And as you can see, we are going to calculate all of those values, and according to that to put it in our HTTP response, which will have its header and its content. As we can see, later we have calculations to split our messages to 1000 bytes. The disadvantage when you're not using fully construction mode, you cannot be precise with your bytes, your specific number of bytes you wish to send, because it's an automatic, fully automatic, and you can change a little bit, but not a lot. If you will use fully construction mode, you can do it by yourself, and if you will put in your setting buffer 1000 bytes, so your buffer only will send 1000 bytes, not more and not less. Of course, in our HTTP header, we are going to inject the decryption key and the N values in the HTTP response header, okay, in order that the client will grab it, extract it, and use it to decrypt the message, the encrypted message we already sent. So as we can see, we are going to send each time 1000 bytes, but it's not fully construction mode, so the computer, the kernel will find a way to do it by itself. It will not ask you how many to send, and that's all. And it will be iterate again and again when we will finish with the send. So in our client side, okay, we will grab. So we will see that before we grab the data, we're going to check if it's in a push ACK, which is the HTTP response, and if it's going to send to our TCP port, which is 80, and additional verification and checking is I'm going to check here if it's the server, if its acknowledge number, which is sent to me, okay, is equal to the length of our HTTP request we sent plus the sequence number we sent at the previous packet. So it will provide more another layer of verification, and if those conditions together will be right, then we can start and grab the data. The first thing that I will ask, if we can find in the HTTP header the server world. If so, we're going to take from it, we're going to grab a couple variable values, the content length and the decryption and the n values. I'm going to touch it more deeply later. It's not really an issue. It's just to grab and to search the data at the first packet we got, because the content length and the decryption and the n values will be stored in the HTTP response header. At the HTTP content, we are going to create condition for it. Okay, after we know what our content length, okay, and I will touch it later because there is some little issues over here how to calculate it correctly. We will say until content 4, which is going to represent the content of our length, will be above 0, or another layer of verification, the last sequence number of our server need to be equal to number we found. Okay, it's because the length of the HTTP header and the length of the HTTP content on the last packet need to be in its precise number we found. It will need to be in the same number we find until it will not be equal. We can iterate ourselves again and again, and in order to verify it, you will see when we will finish it. You can see the printout of it, of the Act 1 and of this number we found. You can see list that they are equal. It's just another layer to protect our while loop and this loop. So each time we are going to iterate in this endless loop, we're going to grab the data, and as you know, we need to combine it meanwhile to one string, and just then we will get the whole encrypted content JPEG with the non-content JPEG, non-encrypted JPEG content. So after we finish with our after we grab all of the data and we finish to iterate, in other words, after the server will finish with its processing the packets, we are going to find our encrypted text. We're going to extract it from the JPEG content, right? And then we are going to decrypt it. Okay? We're going to decrypt it. with our decryption key and the decryption key and the N value. So we can see it over here that we are going to start with some iteration, and we are going to take each value and decrypt it, and just then finally we are going to print it on the screen. So let's see an example how our code is working, and then we are going to dig inside to Wireshark and to our code to demonstrate it live, to explain each step, and that's it. So let's listen to SYN, okay, to SYN request from our client. Let's open Wireshark. Okay, so let's start. We can see that we already find a SYN packet. Now let's put a CMD command. Let's take the help command, which is very big output. Okay, so we will wait. Our reversal is very fast, just because my output on both sides. I wanted to demonstrate you how to encrypt, how to decrypt, all the process. We can see that we got an accurate result. We can see the help command over here. We don't have any issue. Okay, you can see that decryption and the encryption process are very accurate. And what we got and how we translate it and how we decrypt it, and we have all of the process over here. I will explain it. So we can see that we got the HTTP header first, right, with the decryption and the N value. Just a moment. No, it's 20 times to iterate. This is the decryption. This is the N value. I will see it later, and you can see that we inject it in our server name, and later we can see very reliable string of JPEG content, and after 3000 something bytes we are going to grab our encrypted text, which is separated by question mark, each value, the decimal value of it, we can see it, and after we extract it, we are going to put it in two-dimensional array, and then we will decrypt the values. And you can see it over here. After we decrypt it, we are going to bind it together in decimal, and then in hexa we can see it, how it's look like, and then in ASCII. So let's open Wireshark and see what we got so far. So okay, we can see we don't have any errors or retransmissions. So how we going to start? We're going to start as as we see over here. This time we have the regular TCP three-way handshake. We can see the SYN from our client with its IP address 114 at the end. So he already sent a SYN packet, right? Then we are going to reply with SYN ACK with the options we construct, okay, and with the TCP checksum value and the IP checksum value. It's very important, if you are using fully construction mode, to use TCP dump to check your checksum, okay? If not, you will not figure why the session not working correctly, or why you have errors or any issues. So the last packet to end this three-way handshake is ACK or push ACK. Here we can see in ACK, okay, and then the push ACK, which is the client is going to identify in front of us, and we can see HTTP data, which is the hello packet to identify itself. So the server, the client will, we're going to hack it, okay, to acknowledge it, and then to send with the same sequence and acknowledge number. We acknowledge, and the last packet, we are going to request an HTTP request, which is a JPEG content. As we can see, we wish to get something in base 64.jpg, and we provide a reliable text. As you know, to the HTTP header content is going to be end after two line downs. That's mean two 0D 0A twice. Okay, if we're gonna see it twice 0D 0A 0D 0A, it's mean that after it, if you're going to get any response, you will find the data section. Okay, now we are in the response. So the server side will acknowledge it, okay, and then it will process it into its subprocess. It will encrypt the data, and it will send the HTTP response. Inside we can see a couple of numbers we inject, okay, which is the N, the decryption key, and the number of iteration. The content length, it's need to be accurate, okay, and the JPEG content, okay. So meanwhile it seems reliable and everything okay. So next we are going to see and continues to the data. Meanwhile we don't see our encryption string. One point to mention, you can see it's in push ACK. In the real life with servers, it will be just an ACK, okay. So why is that? It's because I didn't send all of the packet from the server side in one time, okay. I just try to split it, and that's what bring it to that every packet that will be out of our server, it will be with push ACK. But if I didn't do it, if I just do it with one sending command, it will do it normally like we see. It's not something that it bother me or I have any issue with it. Just I wanted to make attention for you. So after some packets, we can see after 3 packets, after 2 packets, at the 3rd packet we can see the start of the encryption data we are going to transfer to our server, to our client from our server side. So we can see it still continue and still continue and continue, and we have a lot until the last one, which we will see FFD9, which is going to close this JPEG content and will say, hey, I finished with my transfer of the JPEG content. You can see that each time we will acknowledge it, and we don't have any issue or retransmission with this session. So let's see another live example of our code. So let's run our client side. Now we are waiting for any signal from the server. Let's run the server code, and as you can see, we already done with our TCP three-way handshake process. Okay, now let's run and start with the reversal. So let's take the help command, which is going to be with really big and long output. The server side will encrypt and send to us the the output, and then we will need to decrypt it by ourselves. So we can see that the output is accurate, and we can see it in ASCII mode and as hexa and as decimal after we decrypt the values we extract from our JPEG content. So let's run another command. Let's run the ping command. As you can see, after I press enter, nothing happened, meaning our client didn't send any packet. It's because he feels that there was something strange in our raw input command, such as putty or other gibberish words. So I will need again to put a command. So I put the ping command, and we can see that we got another reliable output. So let's take the do command. Let's try ipconfig. Let's try another one. Okay, so we can see that the reversal is accurate, and let's right now see how Wireshark capture the data. So as we can see, we start with the free TCP three-way handshake. Then we ask from this server and get request of HTTP protocol, which inside it we are going to transfer our CMD request command, which is over here in base 64. Then the server will calculate the output, will encrypt it, and then eventually will tell us how many bytes we will need to take from this JPEG content, and inside it we will we will have somewhere the encrypted data. So we can see it's reliable. It's a reliable message from our server, which we start with regular JPEG message. Of course, we will start with FFD8, which is the opening of the JPEG content, and when we will need to close it, it will be FFD9. So we can see that still we didn't have any encrypted data, and until we will in the third packet we can see the signs of the start of the encrypted data, which is here. So our client needs to be responsible to take all of this data and to be responsible to decrypt it, of course. And as you saw, we got an accurate output. So we can see that we don't have any retransmission or any errors in our TCP session, so it's great. So at the next step, we're going to learn deeply how to achieve the TCP handshake process. We'll investigate it through the output and through the code, and then we will continue to the next video, which will discuss about how to inject our CMD request into our HTTP request, and how we will deal it with our TCP and IP checksum. And at the next videos, we will learn how to encrypt and decrypt the the output of our CMD command request we send to the server. So thank you for watching this video. I hope you will stay to the next videos. Let's explore our TCP three-way handshake process through our client output. Then we'll compare it to our code where each section belong to, and then we are going to see it together with the packet we capture with Wireshark, so we will have more clearly a picture to understand all of it. So let's begin and run the code again. It's on the server right now. Okay, so we started with our three-way handshake, okay, and it's already finished. You can see that we requested to enter an reversal command, so meaning we are will send and push packets. So let's see through our output what is really going here. So as we saw earlier, before we start with the IP function, first we are going to go to the TCP functions. In our case, we will send a SYN ACK packet. It's because we are replying to the SYN request from the server, okay? Then we will calculate the TCP total length, its header and data, and of course we'll add the IP header length, and then we will call to the IP function with the IP total length. After we will call to the IP function with its total length value, we are going to calculate its IP checksum. So here we can see in binary representation all the IP header values, which we already complete its sides to its corresponding sides by the RFC request. So the first 8 bits, the first 1 byte is the IP header and the IP header length and the IP version. So we can see that each one of them is enabled. As we learned in the previous videos, we cannot send enable on the fly, so we add together both values and we got fully 1 byte of value. The next value we can see is the type of service, which will be constant zeros on all of our packets in this video. Next, we have the total length in binary representation. We can see that we completed sides to 16 bits. Next, we will have the identification, also with 2 bytes long, meaning 16 bits of binary values. Next, we're gonna have the IP flex and the fragment. It will be 4T in hexa, which means not fragment in binary. It will be 010, the 3 first bits, and then we are going to complete it to another to 16 bits of value. So we're gonna have in hexa 4T plus another 00. Next value, we're gonna have the TTL, okay, which is going to be 8 bits, meaning 1 byte. Next value is going to be the protocol type. We're going to use 06, which meaning the TCP. The next value is of course the IP header checksum. Meanwhile, is going to be with 16 bits of zeros, and the last values is the source address and the destination address. Each one of them is 4 bytes long, meaning 32 bits long in binary. So 32 bits, okay. So what we did later, we took all of those binary values, construct them together to one string. We count the bits we have, meaning each bit of the string, it's meaning each binary value. So in my code it will be more easier to understand when we talk about byte and bits. So we know that 116 bits is, if we'll divide it by 8, we will have 20 bytes of IP header length. Next, we are going to to take the string and to divide it to 16 bits of binary values. So we can see it over here. If we have 116 bits, in order to make it of groups of 16 binary values, we will divide 116 to 16 and we will get 10 groups of 16 bits of binary values. You can see it over here. The next action is, of course, as we learned in the previous videos, to apply our checksum algorithm on those 16 bits of values. So here we're gonna see all of the calculation, and at the end we are going to ask if our result, the IP checksum result, is greater than 16 bits long as the RFC request. So we will take the bits which make it greater than 60 bits from the left. In our case, it will be the first two on the left. We're gonna cut it from this value, and we are going to make two new variable values. One with the missing bits, okay, with two missing bits from the left, and the other with those two missing bits. We are going to, again, to implement the checksum algorithm on both of them, and then we are going to make sure the result will be in 16 bits long. If so, we are going to make its values, its binary values, we are going to change it to its opposite binary values. So meaning if we had 0, it will be 1, and if we had 1, it will change to 0. So after it, we will extract these bits, convert it into a string and into an hexa, and we will get the result in hexa 96FC. When we will finish with the IP checksum and we will have all our IP header values available, we will pack the IP header values data, and then we are going to continue with our TCP SYN-ACK function. So in our TCP SYN-ACK function, first we calculate our TCP total length, which is mean the header and the data together for the TCP checksum request, and then we are going to do the same actions as we saw at our IP function. We're going to take all of the TCP header and data, and of course some of values that RFC request to the TCP checksum, such as a source IP address, destination IP address, total TCP length, and reserved bits. So we are going to construct them together and convert them to their corresponding binary long values, and then we are going to again split those values into 16 bits long of groups. After we got two-dimensional array with all of our TCP header and data and the values from our RFC request for the TCP checksum, we are going to implement on them the checksum algorithm. Again, we are going to iterate it until we will have no more values on our two-dimensional array, and again we will ask if our last result going to be greater than 60 bits. In our case it's 19 bits long. We're going to take the three bits from the left, and as you can see over here, we're going to cut it and to make new two new binary values. Again, we are going to apply on them the checksum algorithm, and we'll get a result. And again, we will verify it's in 16 bits long. If so, we are going to convert its binary values to their opposite values, and then we will have a result. We're going to extract its bits to string and then to convert it into an hexa, and we will send the before we are going to send, we're going to pack the TCP data with all the values available, and then we have the IP header data packed and the TCP data header and data packed. Then we can send finally the TCP SYN ACK packet. So let's see it in our code, how it looks like again. So here we can see, let's start from our mechanism, which first we'll find if we got a SYN request. So let's copy it. Okay, so first we can see that our mechanism will ask with endless loop if we each time we receive a packet from our OR socket, if we find if we found a destination port which is 80, which we are visualize the listening on it, okay, we meaning the client. Then if with this condition, another condition additional, it's the specific IP address we are searching for, and last another condition to those condition if it's an SYN packet. If so, we are going to we're going to accept it and take the sequence number from the server, from the SYN packet, okay? We are going to increase it by 1, as we can see over here, and then we are going additional to that to take the port number, the source port number of the server, okay, and then we are going to call to the TCP1 function, which is responsible to construct our TCP SYN ACK packet with our new acknowledge number and with the destination number we will need to respond with a SYN ACK packet. So let's see, let's go to our code. So first we can see that we will call to TCP1, which is the SYN ACK packet with two variable values. One is the acknowledge, the second is the port, as you can see over here. the next thing we are going to do is to calculate the size of our TCP header and data, and then calculate the total IP, the IP total length, and then we are going to call to the IP function with the IP total length, and we will get the IP data packet. After, of course, we will calculate each checksum. Next, we are going to, as we saw, to calculate the checksum of our TCP protocol, and we are going to implement the methods to prepare the TCP checksum. As we can see, as the RFC request, first we need the source address, destination address, the reserved, and the protocol number and the length of our TCP, the total length of our TCP protocol, which means the TCP header and its data, and then all the regular variable values we have on the TCP header. Then we are going to copy all of those binary values into string. Let's see how we manage it. So okay. So okay, let's see the output, its corresponding output, and we will have more idea how it's really look like. Okay, this is our IP, and now we are inside our TCP. Okay. So what we have here? First, we are going to calculate our total TCP length, okay, for the RFC TCP checksum preparation. Then we are going to take all of our TCP header values and its data, the header and the data, and of course in our case it's the options, okay, in our TCP header we have another options values, and we cannot forget the RFC request variable values. We are going to store them together into two-dimensional array and split them into 16 bits of binary groups. So then what we are going to do next, we can see it over here. Just a moment. This is our two-dimensional array which we store inside all the TCP header and data values. Then we are going to iterate ourselves, okay? We're going to iterate our A22 8022 two-dimensional array and implement on that array on each pair of binary values the checksum algorithm. Finally, when we will have an result, we can see it over here. We are going to enter to a loop where it's going to decrease and shrink the TCP checksum length if it's greater than 16 bits long. And again, we are going to apply on the new values we create the checksum algorithm. So we can see it over here inside our while loop. And then when we will have the TCP checksum value ready, we can pact our TCP data and just then to send to our server the SYN-ACK packet. Let's open Wireshark and we can see it over here. We send our SYN-ACK as respond to the SYN request from the server. Finally, the server will do two things as we spoke in one packet. It will send a push ACK, which means I'm finished with the TCP three-way handshake process, and additionally I'm sending inside the TCP protocol a data which is our WordPress, in order it will identify in front of us, and then we can start, after we will acknowledge it, with the reversal session. So let's capture some live data from our TCP Handshake process through Wireshark Sniffer. We already start the the program at our client side. Let's run the program on our server side, and the TCP Handshake process is already happened. So let's copy the interesting packet, which is the SYN-ACK. We are going to send as response to the SYN request from the server. As we can see, the server sent a SYN to our port, which we are visualize that we are listening to, which is 80. His source port is 61447, and this value we need to take from our socket, also the sequence number and the options. So let's move to our packet. Let's copy it. Okay. So let's focus first on the two values which are very important, which is the checksum of the TCP protocol and the checksum of our IP protocol. Wireshark calculated, and its data is 96FC, and for the IP and for the TCP is A931. As I told you before, I recommend you to use multiple sniffers and to verify your checksum on both protocols, on the IP and TCP, and of course to verify your checksum algorithm. So if your fundamentals of your algorithm is accurate, you will not have a lot of troubles, but you will need to focus also about what the RSA says about how to calculate the TCP checksum and IP checksum as we learned at the previous videos. So let's see in our code the checksum of our IP, the result of the IP protocol. So we can see here that we start the program. The program recognizes we need to send a SYN-ACK. First, we enter the TCP SYN-ACK function, then to the IP function. We will send in the total length, and the IP checksum result is similar to the result of Wireshark, which calculated during capture the data. Now let's move on to the TCP checksum. So TCP checksum need to be below the IP checksum. So it will be just a moment. Okay, it will be over here, and here we go. The TCP checksum, we have it in binary. Let's copy it and convert it into an X, and we got A931 in X, and which is the same value that the Wireshark calculated. As I told you before, use both sniffers, TCP dump and Wireshark, in order to verify that my checksum is correct with all my packets that I'm sending to the server. So we can see that the TCP dump does not see any problem with our checksums, which is great. If you will have any checksum problem, you will feel it, you will see that the session will not established, and you will have problems during the session. So I recommend you to check each and each step in order that you will not have any problems with it. So the next values is the total length, which Wireshark found it's 52. Let's see in our code if we calculate it correctly. So we can see that the total length is, this is on the second, just a moment. Okay, the IP total length is 44 in hexa, which in decimal it will be 52. So let's see, you can see that we have an accurate result. Next, as you saw, the server sent to us a sequence number, and we acknowledge it by increase its size by 1. That's how we are going to tell the server that we acknowledge the packet and please process to the other packets. Okay, we can see that this value is correct, and we randomly will create a number, a sequence number, and send it to the server. And we can see that the server over here use the sequence number we already randomly created for you. So this was the part 1 when we discuss about how to achieve the TCP handshake process during the full construction mode in raw socket in Python. At part number 2, we will discuss how to inject the CMD request command to our HTTP request header, and how we're going to calculate our TCP data, which is the HTTP header in our case, into our TCP checksum. What is the I think the easy way to make it accurate and very easy to use. Next, we're going to learn how to encrypt the code from the server side and how to inject it into our HTTP response JPEG content. And we will inject the decryption and N values into our HTTP response header. And at the last part, we are going to learn how to decrypt the values and to make our session, the reverse shell, accurate without any problem, because we have here a lot of methods and mechanism, and of course the encryption and decryption, which is very sensitive, so you need to be careful. So that's it for now. Thank you. Let's explore our CMD request, how we inject it into our HTTP request, and the more complicated technique that we learn is how to handle the HTTP request data into our TCP checksum algorithm and to get an accurate checksum result. So let's begin and see live example of it. So we know when we request to press and command, we know that we're already on the stage of starting the reverse shell. So let's type ipconfig, and we already got the output. So let's see what Wireshark captured during this process. So we can see we start with a classic three-way handshake. Then the server will send an push ACK, which is going to identify in front of us. We're going to acknowledge it, and then we're going to send an HTTP request. Inside our HTTP request, we inject our CMD request encoded into a base64. You can see it over here before the JPEG extension. And additional to that data, we have regular HTTP request. You can change it to your values you prefer. And let's see how we achieve it, and if we achieve it correctly through the TCP checksum result. If we didn't get a reliable result, we will not have continued the session with the client, just for mentioning. So let's open the result of our code and see how we handle it. Okay, so we can see that if we wish to send the reversal, we need to find first the TCP push ACK packet, right? So we got it over here. Okay, so we can see it. Okay, so we're going to start with the TCP push ACK function, right? After the TCP three-way handshake process. As we know, first, after we'll enter the TCP function, we are going to calculate the total length of our TCP and IP headers, and then send it to the IP function. Then again we will enter to the IP function, extract from it the IP checksum value, and then packed all the IP header values into packed data. Then we will continue to the interesting function, which is our TCP checksum, and we will need to construct the HTTP request with the CMD request inject and encoded into our HTTP request. And the most again complicated thing here is how to correct the checksum. So let's understand what we have in this output. At this output we have the HTTP header and the HTTP header request with our CMD request encoded to base 64, the TCP header values, and the IP part of the IP header values, and the total length of our TCP header and data value for the TCP checksum algorithm. So we have a total 3088 bits, meaning if we will divide it by 8, we're gonna have 386 bytes, and if we're gonna minus 20 bytes from the TCP header, we're gonna have 366 bytes for the TCP for the HTTP response in our TCP protocol. But it's not enough. Why? Because we have another bits here that is not part of the real TCP header, just part of the TCP checksum, but we already calculate the real size, which is 17A before we get to the TCP checksum. So we calculate our TCP header size and data. So 17A in hexa will bring us 378, which minus 20 from TCP header will be 358 bytes for the HTTP request section. Let's see if it's correct in our Wireshark, and you can see Wireshark found we have 358 bytes for our HTTP request. So let's move on. After we got all of the TCP checksum values, we are going to split it into 60 bits of binary values groups, as we learned at the previous videos. So how many groups we have in 388 bits? We have 193 groups of 16 binary values long. So you can see it over here. We split it for those groups, and just then we started with our TCP checksum algorithm. We implement on those values the checksum algorithm, and it's gonna be long, and because we have a lot of values. And when we will get to the last result, again we are going to make sure, okay, if our last result, the checksum result, will be greater than 16 bits, we're going to minus to cut its values from the left and to create two new values. So over here we cut 1, 2, 3, 4, 5, 6 bits from the left, meaning we had 22 bits, and now we're gonna take those two new values and implement on them the TCP checksum algorithm, and we will get another result which need to be on 16 bits long value, which we also going to check it and verify it, and if so, we are going to convert its binary values into its opposite corresponding values, meaning if we had 1 it will be 0, if we had 0 it will be 1, and we will get the TCP checksum value. So after we understand how the output look like, let's move to the code and see how we can implement it without being mistake, because not all of the time you will get an integer value which gonna divide completely by 16, so it will make the code more complicated to be mistake or to miss some values. So let's just check our TCP checksum and see if we have the same value as the Wireshark. So we got the 7EED as the TCP checksum value, and in Wireshark we have the same value, 7EED. So let's move on to our code and learn how we achieve it correctly. So we can see over here, after we finish with our three-way handshake, and of course we are going to acknowledge the push ACK packet, which is going to identify the server in front of us. We are going to we are going to inject our CMD request into our HTTP request message. Of course, it will be encoded in base 16.4. You can see that each time we have been asking from the user to enter its reversal command, we will find if there is a putty string inside that CMD request. We will ask from the user again to put its reversal command. Next, after we construct the CMD request into our HTTP request message, we are going to add additional data. As you can see, you can change it to your preferred data you wish. Just follow the HTTP request rules, which you know you will need to separate each line. When you declare that you finished the line, you need to provide the RN for each line, and at the end, okay, at the end of this header, in order to identify to declare that your HTTP header is finished, you need to provide 2 RN together, one after line, meaning after this RN there will be no data, just another RN. That's our sniffers and application will know that after this, first of all, that header has been finished, and after it there will be the data section. In our case, we are sending a request, so there is no data section. After it, we can see that we combine all of those strings together to one string, and you will see what we will need to do next with this whole string. So you can see over here that we store the len of our whole string into SD variable. Then we will store inside the II the result of SD divided by 2. Okay. So why I did it, okay, and what the result of it. So additionally, we can see that we define a new 2-dimensional array with the II variable value. So what we did over here, it's very simple. We took all of the HTTP content, okay, and we measure HTTP header request string, okay, into bytes. Okay, we know in ASCII that each letter represents 1 byte. So SD variable will have the length, okay, HTTP length, next II will have the SD divided by 2. It's not matter if it will be complete or not complete, okay. II will always have a number. How you're gonna ask yourself, we will deal if we will not get a complete result, meaning we will have an carry. So what we'll do with the carry, you will see it on the mathematical way I achieve it, and I think it's very short to implement it. Next, we are going to declare new 2-dimensional array, which have inside him number of elements which is the II variable value. So we are going to multiply its element by II. So now what we will need to do is, first, as we saw, we declare the SD variable with the length of our HTTP request byte size. Then we are going to divide this length by 2 and store it in double I. What we wish to find here, I will show you example. Before we are going to see how we implement it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with 10 lines of code. Let's say we'll start with small numbers in order to understand it. 9 bytes long of string, okay? We have A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, 1, 2, okay. A to I, we have 9 bytes long in ASCII mode, okay? So we know that this is HTTP input, okay? So let's follow the same variable values we have. SD will be 9 divided by 2, which the complete number will be 4, but we have 1 is carry, right? And next we are going to SD will be 9, and double I will be 9 divided by 2. It will be 4 with 1 to carry. So now how we are going to we wish to split this string into 2 bytes long of groups, right? And put it in 2-dimensional array. So we wish to do as follow. As you can see, we will have only one value at the end. So how we are going to do it with efficient way without have a lot of lines of code? So let's see. First we are going to create a while loop, okay, which says while SD greater than 2 or SD equal to 2, okay, and we will ask again if SD equal to 2, so II is equal to 1, okay, and then we are going to iterate with the range numbers between II, okay. So let's store the I range, which is the inside range numbers of II, into C, because when we will finish, if we have example like the 9 bytes long of our string, we will need to store the last value, right, in our 2-dimensional array and not be missing with one value. So it will serve us for the future. You will see what I mean. And of course, each time we're going to iterate, we wish to minus SD by 2, because each time we are taking 2 variable values, and we will create 2-dimensional array, right, which it will be with the number of II elements, right? We will multiply it by II, so we will have 4 in our case, right? Only 4 elements to store. Meanwhile, to store the ASCII strings inside, okay. So let's see how we're going to do it. We're going to say that HTTP input 22 with I value is equal to HTTP input new margin that we will create for. So it will be 0 and it will be 2, of course. So let's see what will happen each time we're going to iterate. And here we will put another condition. If SD is greater or is equal to 2, we are going to only then we are going to increase the margin by 2. Okay, and again we're going to iterate the for loop until we will finish with the II. So let's see how it will be in the HTTP, the following HTTP input. So as the first, we know that I is 0, right? C will be equal to 0. SD, which is 9, will be 7, and the HTTP input 22 at the first element will be AB, right? And this is for I equal to 0. Now we know that SD is still greater than 2 or is not equal to 2. So we are going to increase the values by 2, TT and TT2. So we will go forward with the next ASCII values. So let's do another loop. So we know that I is equal to 1 and C is equal to 1 as well, right? SD will be 5 and HTTP input will have a new element inside, which will be, in our case, CD, right? We have 0 to 2 and from 2 to 4. So don't be mistaken here. So we know still SD is greater than 2 and not equal to 2. So we're going to increase TT by 2 and okay. So let's continue. Now we know that I is equal to 2, right? Don't forget that I is 4, so we will count until 4. So I is 2 equal to 2, and then we going to say that C is equal to 2, SD will be 3, right, after we minus it, and HTTP input will have another element, new one, which is GH, right? And now we know that SD EF, I misled you with it. And now we will increase. We know that SD is equal to 3, is greater than 2 and not equal to 2, and we will increase TT by 2 and TT2 by 2, another 2. Okay, so now we will be iterate at the last time. Now I is equal to 3, right? C is equal to 3. SD is not equal to 2, you can see it. So C is equal to 3 and SD is equal to SD minus 2. So our new SD will be 1. And we will store another element which is going to be the last pairs, and we will not have any room because we declare only with 4, right? And we will ask if SD is greater than 2, is equal to 1, and is not equal to 2 and not greater than 2, so we will not move on. And we will finish with the for loop, right? And we will ask again if SD is greater than 2 or equal to 2, so we finish with the while loop as well. Now what we will have is the following line: if SD is lower than 2 and SD is not equal to 0, okay, very important not to be confused. So let's say that TR is equal to 1. It will help us in the next actions we will do. And SD, now we will need to find how to capture the last value. So we will take SD and reinsert him a new value. So we will tell len HTTP input, right, which in our case is 9, minus TTT2, which is the margin we are used, so TT2 we know is equal to, let's see, what is the last TT2, is equal to 8. So we would say that SD is equal to 9, which is the length of our string, right? Minus 8 will be 1, right? So we will say that, where is the code? You got it. We will say that now HTTP input 22. We know C was element number 3, right? So 3 plus 1, it will be 4, right? We will, sorry, just a moment before it, we will know that we will need to insert another element to our two-dimensional array. We will insert string, okay? Then we will say HTTP input Encrypt 22 with C, which was the last time 3 plus 1, which is going to be 4. The 4 element, we have 0, 1, 2, 3, okay? So we insert another new element, okay? And we will have right now 5 elements, A, B, C, D, E, F, G, H, and we'll have A inside, okay? So again, 0, 1, 2, 3, and 4. So HTTP on the fourth side, okay, on the fourth location, sorry, will be equal to HTTP input, our original ASCII string, to TT2, which is 8, right? And we'll take 8 plus 1, which is 9, TT2 plus ST, as we can see it over here. So, meaning we will take the last value, okay, from 8 to 9, which is this value, and we are going to store it inside our fourth element. So HTTP input 22 will be look like as follows. And we will finish with our mathematical method, if I can say it, to get over problems if we will not have an HTTP header request content length which is not divided completely by 2. So that's how we are going to fix it without any issues. So if you will take big numbers, let's say 321, okay, let's divide it by 2, and we know we will have 160 groups of 2 bytes, right? So let's double it by 2, and we know that the left 1 byte, the delta between them, will store at the last with new element in our two-dimensional arrays at the last place. So that's how with 7, 8 lines, we are going to make it accurate without any problems. So on the next code, you can see after we got a fully output, which is divided into 2 bytes of groups of elements, we are going to take each element inside it, okay, and we are going to convert them into an binary values, and then we are going to construct them all together into one string, okay, and just then we are going to send this one string into our TCP push ACK function. So how we're going to do it? It's very simple. We are going to iterate the number of elements we have in our two-dimensional array and take each value we're going to extract from it and store it into an array, and then we are going to iterate this array with all its elements and combine those binary elements together and send them to our function. Let's see the output of it. Here we can see the calculation of our TCP request. We have a lot of values. We have 3000 something bits, 3088 bits. So you can see that after we divide all those ASCII, just a moment, you will see right away. Okay, so we took the ASCII string, which is the HTTP request, right? And we divide it into two, you can see two bytes of groups. And then we are going to convert them into binary values, right? So we will have 16 bits of binary values of groups, and then we're going to send them into our TCP push ACK function, and to combine this data as one string with our left TCP checksum and with another TCP checksum variable values, which are the TCP header values and the additional TCP checksum values from the RFC request, such as the IP address, the destination address, the TCP data length, and the reserved bits. So we're going to take all of it and then we're going to calculate it into our TCP checksum algorithm. Just then we will have an TCP checksum value. Let's see the result of it. You can see how many elements we have here. It's a lot. Okay, so this is the value. Let's check it. We already checked it. It was 7 EED as well, with as the same value we got from our sniffer. So that's all for this chapter. Of course, after we have all our data, we are going to send it. Let's see, it's very simple. Let's see the mechanism. So after we have our data, you can see it over here, we are going to call to the push ACK TCP function with the new acknowledge, new sequence number, port number, the HTTP input, the string itself, and its binary representation in one string, and then after we will get back the values, back the TCP and IP, we are going to send our push ACK, and then we will need to prepare ourselves to get the encryption the encryption string from our server. Thank you for watching this chapter. Let's explore our server side and its main functions, which one of them, of course, is the encryption through the private RSA algorithm, and the injection of the encrypted string into the JPEG content as HTTP response for JPEG content, and how we can handle the split to do it an accurate split for 1000 packets for all of our response packets, and additionally we will transfer and inject the decryption and the n values in order that our client side will successfully open the encrypted string. So let's see an example. Just want you to mention that in all of the previous examples I used small prime numbers, and for this example I used not much bigger, but bigger prime numbers, so to see if our code will be accurate and the speed of the encryption and decryption. So let's see an example, and we will investigate each stage together. So let's start. Let's run the ping command. We can see that we already called to our private RSA algorithm, and we will encrypt each value and store it into one string. We will separate each encrypted value into one string with question marks. We will explain it later, and you can see the difference from the previous videos to this video, that our encrypted text now is much bigger than it was before. So you can see that 13 became to 792, 10 became to 100, 85 became to 804, 115 became to 539. So as we learned at the RSA algorithm when we wrote it, is much it will be more good for you when we will use and higher core prime numbers, and of course you will need to check and verify each key pair of keys. You will find the encryption and decryption keys during each value you are going to encrypt and decrypt. Sometimes you will have an issue when the encrypted text will be identical to the original value you encrypted. So you will need to verify all of the combination of the encryption and decryption keys. We talked about those issues before. So our private algorithm will find the best press key for this action. So let's start with the beginning of the code, and later we will cover each step. So first we will create the socket, which is a regular TCP socket. We can see it, and then we are going to connect to our server to port 80 as destination in our case, and this tiny line will eventually create and establish the connection, and will handle for you the TCP three-way handshake. Then we are going to identify ourselves with the WordPress hello, and then we are going to receive the data from the client, extract from it the command prompt request, which was encoded in base 64. We will decode it. Then we will open a subprocess, run the command, save the output. Okay. Then the interesting thing, we will iterate the ASCII string we got from the output. We'll take each byte, meaning one word, one ASCII word, one ASCII, not the word, it's one ASCII letter, okay? Each letter, we're going to store it in our two-dimensional array, convert it into an X, and then into an integer. Later, we will call to our private RSA algorithm and its method with two prime numbers, 31 and 37, and with a third value, which is just for checking the first encryption and decryption function, which is going to do on over this value. We're going to encrypt and decrypt with the pair of values, the encryption and decryption keys, and the n values we're going to get, and then we'll do the same iteration for each number we have in decimal in our two-dimensional array. So after we will get the inc and dec and n values, we are going to encrypt our text. We are going to iterate the two-dimensional array, extract from it the value, okay? We are going to here we can see it. We are going to encrypt it as we learned in the previous videos, and then on the last action we are going to store it into one string, okay, which each encrypted value which is going to be stored there is going to be divided by question mark from the right and from the left. So let's see those stages in our output. We can see that we took each value, encrypt it, and store it with question marks in one string. So let's see sorry for that. Okay. And additionally, we will save this string into an array for internal verification and internal actions, which I will explain later. So after we have the one string, encrypted string with the question marks inside it, we will need to inject it into our HTTP response, right? So what we're gonna do first is to create a reliable JPEG content, which is signature start with FFT8. Let's see how Wireshark see it. Let's see the response, the first response. So we can see the first response which we sent from our server side is look reliable. We can see the HTTP header response. You can see inside the server we inject the it means that inside the HTTP header response we inject the numbers of iteration that the client will need to iterate. I will explain it later what it means. The decrypted value and the decryption key and the n value in order to decrypt the encrypted string we will get. Next, we can see that we send unreliable JPEG content, and just after, let's see how many packets, just on the third packet we can see that we will start with our encryption string, and its signs will be to know that we will take the correct encrypted text string, sorry, this is the sign we will create for us in order to know that this is for the start, the beginning of the encryption encrypted text, and as well for the end of the encrypted text. So we can see that the last packet we send, we will close the encrypted text by the same signs, and of course we will close the JPEG content with the FFD9. So let's see it on our server side. We can see that we over here, just a moment, in H15 we are going to construct all of our string. H represent all of the HTTP response string, which inside we can see we inject the DEC and the N values for the decryption process at our client side. Next, H11 is the JPEG, the reliable JPEG content, and we can see that at the end we plus another 3000 bytes of the A letter. Next, H10 is going to represent the start, the beginning of our encryption text, and then Q22 is our encrypted string with the question mark inside it, as we saw earlier. Okay, then we will need to close it, right? So H13 will be the signs of that this string, encrypted string, is at its end. And for the last value is of course H12, which means the FFD9 in X, which is going to represent to close the JPEG content. So in order to divide all of those packets into in order to divide all this one huge string and make it reliable, first we need to respond with HTTP header response and part of the JPEG content. And in order to divide all of those content, all of this content, and the first packet content, the HTTP header response and its part of the JPEG content into 1000 of packets of 1000 bytes of packets, we will need to do some mathematical method, which is very simple. As you remember, in the first packet we send the HTTP response and part of the JPEG content. So in order to know how much you can send in one packet, you will need first to measure your HTTP response header and minus it with 1000 bytes, and then with the delta you will need to put your JPEG content and ensure it will make reliable for your client. So you can see here all the calculation. I think you will be more accurate than me, but it's not right now the important thing. The important thing here is to encrypt the text, to inject it correctly, and to send it. So we can see that I'm going to iterate with while loop and to send with margins of 1000 of bytes of all our packets until we are going to finish it. So This was the server side and our encryption side. Let's see how we managed to capture the decryption and encryption keys. So we can see when we call to our RSA algorithm and its method, we first encrypt our text value in decimal, which is 102 we sent, and we are going to do some calculation on it. You can see that we have plenty of encryption keys and its corresponding decryption keys. We are not going to delete none of them until we are going to check each one of them, which will be the most fit for all of our values for the encryption process. After we found it, we will send back the values, and of course we will need to be responsible to send the decryption values and the end values injected into our HTTP response header, as we can see. So this was our server side. Was very short. There is not a lot to talk about because we already learned how to do most of those actions. So at the next video we're going to learn how to capture the data with the client side, how to decrypt it correctly, and how to transform it into an ASCII, combine of all of those ASCII letters together to one string, and then to print it out to the screen. Thank you for watching this video. I'm waiting you for the next video.